one.
Hello, we are here on representing Operation Starfish Prime, and we'd like to talk to you about a follow-up study we're proposing that could help change the world.
So as you can see here, clearly in this graph, this goes between the years 1960 and 2010. Obviously, this trend that we see has been happening since the Industrial Revolution. Before this, there's been an incredible upward trend in the amount of CO2 that is in our atmosphere. And this is largely due to development of infrastructure and the Industrial Revolution, which has led to increased emissions worldwide. But so why do we care? I mean, on paper, CO2 just looks like a gas. It looks like something that we learned in chemistry class, and we're like, oh yeah, that's kind of neat, and then don't remember ever again, and it's gone. However, CO2 has a daily impact on all of our lives and is a very global issue. So first off, global warming is incredibly impacted by CO2 emissions. CO2 accounts for 82% of global emissions of greenhouse gases, and that overall contributes to global warming and the increase of temperature worldwide, which of course is a horrendous problem that we're dealing with today. And another interesting thing about this is that at the same time as we are dealing with, we are producing so much deforestation, we are also reducing our capacity to deal with it, like through deforestation. And so we're both, at the same time as we're putting all the CO2 out, we're also reducing our world's innate capacity to deal with it. So all of this leads to more CO2 in our system, in the world, and that leads to CO2 poisoning. So in humans, the symptoms of CO2 poisoning include irregular breathing, dizziness, nausea. It's lethal in very high doses, around 70,000 parts per million for humans, which is incredibly high concentration. That's the immediately lethal dose. It is damaging to humans at lower doses at about 30,000 parts per million or so. However, other different organisms, more than humans, especially smaller organisms, have a higher or lower tolerance to carbon dioxide. And if they have a lower tolerance, that means that parts that to us might either seem invisible, we might not even notice the effects, or it's just slight effects, such as like nausea or dizziness, can have very drastic effects on them, and that can lead them, if they die or for their habits to change, for ripple effects that go through an ecosystem and our world, and can bring down a whole chain of organisms that lead back to us and damage our world overall. And so this is just a list of various what the effects of different levels of exposure of carbon dioxide, just to show how many different kinds of effects there are. It ranges from the normal outdoor levels, about 250 to 350 parts per million. Then about an urban environment is 350 to 1,000. And then it goes on, it goes increasingly bad symptoms from drowsiness and poor air to like headache, sleepiness, poor concentration, and then death at the very end at the highest concentrations.
So our original experiment was we set up an ecosystem and an eco-column so that we could observe what happens with this and other gases and how the organisms respond to that. Unfortunately, our organisms all died, but we got a lot of good data out of it. Yes, and the name of science they died. So these were our findings. The most immediately obvious finding was our carbon dioxide. Our carbon dioxide started high, about 10 times what you normally see on Earth, and just skyrocketed after that, approaching nearly 1% of the air being carbon dioxide. Also, this is when the animals started dying out en masse, so we think it's reasonable to believe that the animals were killed off by this carbon dioxide. And we also noticed when we graphed these that along with the carbon dioxide spike came a drop in the pH. As you can see, carbon dioxide spikes, pH drops. And this is interesting because it could be indicative of carbon dioxide dissolving into the water, which would cause a drop in pH. And if this is the case, that is carbon dioxide that isn't poisoning our animals, and instead is being held harmlessly in the water until the carbon dioxide levels go down enough to breathe them again. So if the carbon dioxide levels are dissolving, then that is fantastic because we can use that to help save our animals. So our question is, would the addition of a body of water dampen fluctuations in ambient carbon dioxide levels? If we had more water, would that help absorb the carbon dioxide? And our reason for believing this is because when carbon dioxide dissolves into water, it forms carbonic acid. And because of this, when carbon dioxide dissolves into water, it doesn't just sit there dissolved, it turns into something else. So more and more carbon dioxide can enter the water and dissolve, allowing water to store a very large amount of carbon dioxide, which again could help save animals.
Yeah, so to look at all of this and kind of tie this all together and develop our thesis further, our ideas further, we decided to set up an experiment. So the first step that we did was to set up 4 ecocolumns. And we'll get into the differences between those in a minute and explain those in a second. So, set up 4 ecocolumns, make sure to keep put terrestrial plants in, and to make sure that the balance between carbon dioxide producing organisms, such as fish, crickets, etc., organisms, balance out with the terrestrial plants that are there, which we did not do so well in our ecocolumn, and ended up with it just becoming a barren tube of plastic and devoid of life. So. We make sure that balance is good, and then we also construct.
Yaneli Flores, can you come to the front desk? Yaneli Flores.
Background. Oh, excellent. We can continue. So, back on track. We have identical indentations lined up with non-permeable, rigid materials such as clay, and all of the key part of these is that they ought to be completely equal in order to eliminate the lurking variable of changes in shape, length, volume, because we want them all to be volume and that to be constant between each of our 4 ecocolumns in the study. Then we would allow the CO2 to stabilize, so we make sure all ecocolumns are starting from the same place. And then, this is the key part, we fill each ecocolumn with varying amounts of water. The first one we fill with no water is our control. Then the next one we fill 1/3 of the indentation with water, the next 2/3 of the indentation with water, and the last one completely with water. And this is how we get a variety of volumes of water, and we can see directly the correlation between volume of water and the impact on the CO2 and acidity in the water. And yeah, then of course we just record our results every day for 3 weeks, and so we can see the patterns in the study and come to a conclusion at the end. And so our hypothesis is that when the volume of water increases, it has a higher capacity to store ambient CO2, and therefore will dampen fluctuations in the ambient CO2 levels of the terrestrial chamber. So to get this, our expected results are that ambient carbon dioxide levels will be lower, and fluctuations therein will be more dampened than in ecocolumns with larger bodies of water, for all the reasons we described above.
Conversely, we would expect the amount of carbonic acid in the water to increase, which would indicate that the carbon dioxide is in fact dissolving into the water, that the water is what's causing this, and that some aliens aren't just teleporting it out of here.
Great point. And building up that, as you just said, conversely, which is a perfect segue, these two must be completely correlated, because if we don't see that the amount of carbon dioxide are lower with areas with larger bodies of water, and if we saw that it was lower in areas with larger body of water, but the pH was not increasing, then that would be a little odd, because there's a lurking variable or something else, another factor that is affecting our results, and we'd have to do more studies to conduct that, or to discern that answer.
So this could have many applications if it pans out. So first off, we could use bodies of water to mitigate carbon shocks in ecocolumns or small ecosystems, areas where carbon dioxide can spike massively, and that can kill off everything inside if you're not careful. If this works, then adding water to those ecosystems would allow those organisms to survive and to overcome the carbon dioxide shock.
Mm-hmm. And at the same time, if this study is successful, it might find some immediate application in areas of the world right now that already have a high concentration of CO2. For example, in the Amazon basin, in countries such as Brazil, they have a very, very difficult problem with local CO2 pollution and local CO2 high concentrations. And if the water sink proves to be effective, especially if the volume of water proves to be effective rather than cover a surface area of water, then that could be extremely applicable in those settings where we need to deal and dampen the effect of high concentrations of CO2.
And finally, this could serve as an impetus for further research into using water as a carbon dioxide battery to isolate it and to transport it, so that we can isolate carbon dioxide coming from industrial sources such as pollution and neutralize it, so that when we do release it to the environment, it's no longer a greenhouse gas and it's no longer hurting our world. So for all these reasons, we hope that you will help us with our project to curtail global warming, and we hope to hear from you soon.